In this video, we're going to talk about how to graph absolute value functions and define key features. So remember, what is an absolute value? An absolute value tells you the distance of a number from zero on the number line. So that's why absolute values are always a positive number. So if we take the absolute value of a positive number, that's equal to that number itself. So for example, the absolute value of 3 is 3 because 3 is 3 units away from 0. The absolute value of a negative number is the opposite of that number. So, for example, the absolute value of negative 4 is 4 because negative 4 is 4 units away from 0. The absolute value of 0 is always 0 because 0 is 0 units away from 0 on the number line. So today we're going to graph absolute value functions such as f of x equals the absolute value of x, and we're going to determine some key features of the graphs. So the key features we're going to talk about are domain and range, intercepts, symmetry, the vertex, and any maxima or minima. So you may remember the absolute value parent function back from when we studied parent functions a few lessons ago. So you'll notice that absolute value functions are very similar to parabolas, right? We have a lot of the same features and a lot of similar things going on. So for example, we have a vertex, okay? So the vertex is going to be the highest or lowest point on an absolute value function. If the absolute value function opens up, the vertex is going to be a minimum value. If the absolute value function opens down, the vertex is going to be a maximum value. So we also have the axis of symmetry. Remember, the axis of symmetry is not something that's going to show up on our graph when we graph it in Desmos. It's a line that we can draw in ourselves. It'll be a vertical line about which the graph has reflectional symmetry. And what happens is the axis of symmetry actually passes through the vertex. So what happens is the x-coordinate of the vertex can actually tell us the equation of the axis of symmetry. So for example, in this function, you can see that the vertex here is at negative 3, 0. So x equals negative 3 is going to be the axis of symmetry. Another way that you can figure out the axis of symmetry is to take the expression that's inside the absolute value and set it equal to 0 and solve for x. So for example, if I say x plus 3 equals 0 and then I solve for x, I would also get x equals negative 3. So the x-intercept of an absolute value function will occur where the graph crosses the x-axis. So some absolute value functions will have two x-intercepts, or you may have absolute value functions that don't have any x-intercepts. And so the quickest way to identify an x-intercept is to graph the function in Desmos and then click on the points where the graph intersects the x-axis. So let's try this function that we have right here in Desmos. So we have the absolute value of x plus 3 minus 4. So if you want to type in an absolute value, you can click Shift and then use the button above Enter on your keyboard, or you can use the keypad in Desmos. If we click the absolute value of a, see how the absolute value signs show up. So then we're just going to type the part that's inside the absolute value. So we have absolute value of x plus 3, and then I have to click out of it to close the absolute value. And then I can type my minus 4 on the outside. So what you can do now is you can just click on those two x-intercepts in Desmos and it'll give you the coordinates. So that's how you know that negative 7, 0 and 1, 0 are the x-intercepts. Another way to find the x-intercepts is to set your equation equal to 0 and solve for x. Because notice that the y-coordinates will be 0 at the x-intercepts. But I know that we don't know how to solve absolute value equations just yet. So for now, you can just graph in Desmos and click on the points. So the y-intercept of an absolute value function will be where the graph crosses the y-axis. Once again, this is pretty easy to identify in Desmos because all you have to do is click on the point where the graph crosses the y-axis. And so you can see that 0, negative 1 is going to be the y-intercept. Notice that x equals 0 at the y-intercept, so you can also find it by plugging in x equals 0 in your equation and solving for y. So let's look at all these key features and how they relate to the absolute value parent function, f of x equals the absolute value of x. So the parent function will have a domain that goes from negative infinity to infinity because notice that this is going to include all real numbers for x. Just like parabolas, the range is going to have a specific endpoint, right? So notice that this starts off at 0 and then includes all the y values above that. So the range is going to go from 0 to positive infinity. The x-intercept and y-intercept are both at the origin, so at 0, 0. And that's also the location of the vertex, okay? So the vertex will be at 0, 0. Since this absolute value function opens upward, it's going to have a minimum at the vertex, and the minimum value of the function is the y value, right? So it's going to have a minimum of 0 at x equals 0. Also, this graph will have reflectional symmetry with respect to the y-axis, which is x equals 0, because notice that that is the x-coordinate of the vertex. And just, keep in mind that absolute value functions have very similar characteristics to our quadratic functions. So now let's try graphing some examples. Let's start off with f of x equals the absolute value of 2x minus 4, and let's define its key features. So let's start off by figuring out some points. So I'm going to use some x values, and I'm going to plug them into my function and use those to figure out some points that I need to graph. So I'm going to plug in the x values like -3, -2, -1, 0, 1, 2, and 3. Okay, so the way to graph these by hand, I'm going to go ahead and plug in these x values and then solve for y. So I have the absolute value of 2 times -3 minus 4. And so that's going to be the absolute value of -6 minus 4. Well, the absolute value of a negative number is the opposite of that number. So that's going to be 6 minus 4, which is equal to 2. Okay, now let's plug in -2. So we have 2 times -2 minus 4. So that's the absolute value of -4 minus 4. And that's going to give us 4 minus 4, which is equal to 0, right? And then we have the absolute value of 2 times -1 minus 4. And so that's going to be the absolute value of -2 minus 4, which is equal to 2 minus 4, which is -2. Okay, so you can keep doing this and using that to find the points. Some people actually like to use Desmos. And what you can do in Desmos to get this table of values is you can just type in the absolute value function, right? So we have 2x and then click out of it. And then we do minus, whoops, you do -4. And then what you can do is you can click on these points to figure out the coordinates, right? So at 0, we click on our function at x equals 0, and that tells us -4. So you can figure out the coordinates of these points that way also, if you prefer to do so. You can do 1, -2, and then sometimes you have to scroll a little bit to get at exactly 1, but this way works also. Another way to do that is if you have your TI calculator, you can also use that. And remember, you can get the table of values. So you can go to y equals, and how you get the absolute value to show up on your TI, you need to use the math menu and then arrow over to the number menu. And you see it says ABS and then parentheses. If you hit enter on that, then your absolute value will show up. Okay, so we can do 2x. And then remember, go out of the absolute value and then do -4. And then if you click second table, you have your table of values, right? So let's find where we were at. So we were here. And so we have, let's see, 2, we have 0. And then at 3, we have 2. Okay, so you can get the table of values any way that you want. You can find them by hand, you can use Desmos, or you can use your graphing calculator. Okay, so once you have all these points, you're going to need to graph your function. So let's see, we have -3, 2, -2, 0, -1, -2, 0, -4, 1, -2, 2, 0, and 3, 2. And the nice thing about having your graphing calculator out while you are graphing these functions is you already kind of know what the graph is supposed to look like, right? So that way when you connect these, you kind of know, it's supposed to be this V shape and that it opens up and things like that. Okay, so now we need to define its key features. So when you're looking at key features, I really think that Desmos is very helpful because it gives you a really nice idea of what the graph is supposed to look like. And when you're figuring out things like intercepts, like you can see here, my sketch isn't great, and so it's kind of hard to see where the graph crosses the x-axis. But in Desmos, you can just click on those points and it'll tell you the exact values. Okay, so the domain, you can see that all real numbers are included for x. So I'm going to say the domain goes from -infinity to +infinity. The range, well, it looks like the lowest y value is here, right, at -4. And then it includes all y values above that. So I'm going to say -4 to infinity. The x-intercepts, I'm just going to click on them to get the coordinates. So I have two x-intercepts. I have -2, 0, and 2, 0. And then to find the y-intercept, I'm just going to click on that, and the y-intercept is at 0, -4. The y-intercept also happens to be the vertex, so I'm just going to write that down, 0, -4. And since this absolute value function opens up, it's going to have a minimum. And remember, the minimum is going to equal the value. So it has a minimum of -4 at x equals 0. Okay. And to figure out the axis of symmetry, we're just going to look at that x coordinate of the vertex. So it has reflectional symmetry, right? All our absolute value functions have reflectional symmetry. So reflectional symmetry with respect to x equals 0, right? Because that's going to be that line that we can draw in that represents our axis of symmetry. Okay, so now let's practice with some more examples. So let's try graphing the absolute value of x minus 4 minus 3 and define its key features. So the points that I'm going to use 1, 2, 3, 4, 5, 6, and 7. Okay. And let's try this one on the graphing calculator actually, because I like how the table of values shows up. So I'm going to clear and then I'm going to do math and then number and then hit enter on absolute value. And then we do x minus 4, right? And then click out of that and then do minus 3 and then do second table. And if I scroll to the right place, it's going to give me all the values I need to create this graph. So I have 1, 0, 2, -1, 3, -2, 4, -3, 5, -2, 6, -1, and 7, 0. Okay. And then if I click graph, it's going to give me a nice visual of what my graph is supposed to look like. So let's go ahead and graph that on our coordinate plane. So we have 1, 0, 2, -1, 3, -2, 4, -3, 5, -2, 6, -1, and 7, 0. You can kind of see the symmetry start to show up when you're plotting these points, because you'll notice that sometimes the y values get repeated and you'll start to see the symmetry in this graph. Okay, so now let's define its key features. So for key features, I'm actually going to use Desmos to help me out. So I'm going to go here, do absolute value, and then I do x minus 4, and then I'm going to click out of that, and then do minus 3. Because the graphing calculator doesn't have that feature where you can just click on a point and it tells you the coordinates. You kind of have to move the cursor around. So I like to do this part in Desmos. So we include all x values in the domain. So it's going to go from -infinity to +infinity. Notice that the range has a lowest point. So the lowest y value is going to be -3. So it's going to go from -3 to +infinity. The x-intercepts, let's go ahead and click on those. So we have two x-intercepts. It's going to be at 1, 0 and 7, 0. The y-intercept, if we click on it, that's going to be at 0, 1. The vertex, so if we click on the vertex, it's going to give us the coordinates. So we have the vertex at 4, -3. This absolute value function does open upwards, so this has a minimum. And the minimum will be the y value. So it has a minimum of -3 at x equals 4. Okay, and so with symmetry, we know that our absolute value functions have reflectional symmetry. So it has reflectional symmetry with respect to, I'm just going to abbreviate that, the line x equals 4, right? Because we just look at the x coordinate of our vertex to figure out where it has reflectional symmetry. All right. So now you can go ahead and pause the video and try doing this example on your own. So here I have the coordinates of this graph all written out. So you can see I have these different x values, and you can get the coordinates from your graph in Desmos. And then what we can do is define its key features from the graph in Desmos. So notice the domain is going to include all real numbers. So it's going to go from -infinity to +infinity. The range starts off at -2 and then includes all values above that. So that's going to go -2 to +infinity. The x-intercepts, if I click on them in Desmos, notice that the points are -5, 0 and -1, 0. The y-intercept is here at 0, 1. The vertex has the coordinates -3, -2. And since this absolute value function does open up, the vertex is going to be a minimum. So this graph has a minimum of value of -2 at x equals -3. And also that means that it's going to have reflectional symmetry with respect to the line x equals -3. So let's try this example. Let's try graphing f of x equals negative absolute value of x minus 5 and define its key features. So I'm going to use these x values to create my graph. So I have -2, -1, 0, 1, 2, 3, and 4. Okay, so if I go ahead and go to Desmos, I'm going to use Desmos on this one to help me out. So I put my negative in front. And so I have negative and then the absolute value of x, and then click out of the absolute value and then minus 5. And you can see this is what my graph is going to look like. So if I figure out the points, so I can see at -2, I'm here at -7. You have to scroll a little bit to get exactly there. There you go. -2, -7. At -1, I can see it's at -6. 0, I'm at -5. 1 is here at -6. 2 is -7. And then 3 is -8. And 4 is -9. Okay, so if I recreate my graph over here, I have -2, -7, -1, -6, 0, -5, 1, -6, 2, -7, 3, -8, and 4, -9. Okay, so I'm going to connect my points and I know that this is what my graph looks like because I can see it in Desmos. So now let's define its key features. Okay, so the domain, it's going to include all real numbers, right? So it's going to go from -infinity to +infinity. The range is going to be interesting because this graph actually has a highest point, right? So it's going to be -5 and it's going to be all values below -5. So actually the lowest value in my range is going to be -infinity, right? Because it's going to go from -infinity up to -5, right? Because remember, we go lowest to highest when we're talking about domain and range. Okay, so now we're looking for x-intercepts, and actually there's no x-intercepts, right? Because this entire graph exists below the x-axis, so we actually have no x-intercepts, okay? And that does happen sometimes with absolute value functions. So we would say there's no x-intercepts. It does have a y-intercept, right? That y-intercept happens to also be the vertex. So it's at 0, -5. So the vertex is at 0, -5. So this graph actually opens down, so it has a maximum value. So it has a maximum of -5 at x equals 0. Okay, and it has reflectional symmetry with respect to x equals 0, right? The x coordinate of that vertex is going to tell us the axis of symmetry. Okay, so we can graph absolute value functions to identify several key features of the graphs. Some of the key features you want to pay attention to are the domain and range, intercepts, the vertex, the axis of symmetry, and any maxima or minima.